Good afternoon. Today I'm going to talk about broadband internet performance and our effort to measure it from the gateway. I'm a fourth-year PhD student at Georgia Tech. I work with Professor Nick Feimster, and this is joint work with the University of Napoli and the University of Paris. Broadband usage is proliferating around the world. There were estimated to be more than 500 million users at the end of 2010, and this number is projected to grow in the future. So naturally, there's a lot of interest in knowing how these networks actually perform. Access ISPs are interested in knowing what performance their customers are seeing and whether they can get better visibility into the access network, and maybe that'll help reduce service calls. Content providers are interested in knowing whether the optimizations that they do to routing and traffic engineering actually delivers a better user experience. Consumers and regulators, they're also interested in knowing whether access ISPs actually deliver on their promises. However, measuring home networks is not easy. As a motivating example, consider throughput measurement. In a typical home network, you have multiple devices that connect to the gateway device through the wired or the wireless interface. We profiled one such user in Atlanta, an AT&T DSL user with a 6 megabits per second down and 512 kilobits per second up plan. We ran a speedtest.net test through the wireless network, and we saw that this user was getting 4.4 megabits per second down and 140 kilobits per second up. We then ran the Netializer test from Berkeley, and we saw 4.8 megabits per second down and 430 kilobits per second up. As you can see, these numbers are not only different from each other, but they're also quite different from the actual service plan this user is supposed to be getting. The reasons for that are many. The most important ones are that these are not continuous measurements. These are not numbers that you obtain over a period of time. This is a single snapshot of the state of the network at that time period. They're also affected by confounding factors. In this case, the wireless network, and also any possible cross-traffic in the home network. So we propose that these measurements be conducted directly from the home router itself. We instrumented a home gateway, and we deployed it in this user's home over a period of 1 month. And we saw an average of 5.6 megabits per second down and 460 kilobits per second up. This number tallies more closely with the service plan rate. So doing measurements from the gateway enables periodic measurements, continuous periodic measurements, and it can also account for confounding factors. It takes the wireless network out of the picture, and it can also account for cross-traffic inside the home. So we present the BISmark Platform, which is our effort to measure the home and access network. The BISmark Platform consists of the BISmark gateway, which runs periodic measurements to nearby servers and also the ISPs network. This gateway is based on the OpenWRT firmware with a custom measurement suite. The measurement suite runs periodic active measurements of the access link and the home network, and it measures metrics like throughput, latency, packet loss, and jitter. Currently, we support the Netgear 3700 router, but we have plans to support other platforms. The measurements that these routers conduct are uploaded to our central server in Georgia Tech and can be viewed at networkdashboard.org. So I'm going to show a few examples of real-world measurements that we have been conducting over the past few weeks. So first up, throughput. So to measure throughput, we use netperf over TCP to a nearby server, which is in Georgia Tech. And it uses single and multi-threaded tests in order to measure the download and upload throughput. So this user that you see on the graph is an AT&T DSL user with a 3 megabits per second down plan. So these measurements are over a period of 3 weeks, and and the router conducts these download measurements every about 2 hours. What we see here, the two lines denote the two different kinds of tests, the multi-threaded and the single-threaded test. The green line is a multi-threaded test, and the blue line is a single-threaded test. So what we see here is that the multi-threaded test shows us about 2.6 megabits per second down, and the single-threaded test gives us about 2.4 megabits per second down. This is another user in Atlanta. A Comcast user subscribed to the performance service plan. This user sees about 18 megabits per second down. And interestingly, both the single-threaded and the multi-threaded tests show very similar numbers. These tests are conducted over 15 seconds, so what you see here is very possibly just the power boost numbers. We also do latency measurements. We measure latency to 3 different servers, one in Georgia, one in California, and one in Italy. What we see here are the latency measurements from this Comcast customer's home. And interestingly, you already see some interesting trends here. Around the 20th of September, you see spikes across all the 3 latency measurements. Another aspect of latency we measure is the last mile latency, which is the latency from the router to the first IP hop in the ISP's network. We obtain this IP hop by running a trace route and extracting the first non-NATed IP address, and we run a ping to this address. So this is a plot of the last mile latency for the same Comcast customer. Please note that the y-axis is log scale, and we see that the baseline latency is about 8 milliseconds, but it can go up to 18 milliseconds. The last mile latency is important because this latency is seen by every packet that goes out of the home router. So all these measurements, so we also, beyond throughput and latency, we also conduct DNS lookup and trace route measurements. All the parameters are completely configurable from the server, so the duration, the frequency of the tests, they can all be controlled from the server itself. And these routers also come fully equipped with a whole host of measurement tools like iPerf, curl, shaper probe, fping, HTTP ping, and TCP traceroute, Paris traceroute, NSLookup, and DITG. As I said, the parameters of all these tests can be configured at the control server. Beyond that, we also offer the ability to run customized measurements. The routers periodically download scripts from a central control server over SSL and run these scripts periodically every 10 minutes. So each router could, in theory, run custom tests that uses any of the network measurement tools that are already provided in the server, and we also offer the capability to upload results to the central server. These routers are managed from a control server at Georgia Tech, which listens for periodic heartbeats from the routers. And it also pushes configuration updates and the on-demand test scripts, and it also receives the measurement data from the routers. The measurement data is stored in a Postgres database, which is used by Network Dashboard to plot the graphs that I showed you earlier. The measurement servers host the server side of the measurement tools that I mentioned. So we have 3 of these, one in Georgia Tech, one in the University of Napoli, and one in the University of Cape Town. And in order to add geographical diversity and to reduce the stress on our current set of measurement servers, we are planning to commission measurement lab servers soon. Now the hardware. So the BISmark router is based off of a Netgear 3700 V2 router with an Atheros chipset and a high-end MIPS processor with 16 megabytes of flash and 64 megabytes of RAM. It has gigabit LAN Ethernet and a 2.4 gigahertz and a 5 gigahertz radio. The firmware is based off of OpenWRT with Lucy as the web interface, which allows easy configuration. And the box comes IPv6 capable. So it's pretty much a plug-and-play router in the home network. So moving on, I'm going to show some interesting results that we have been able to observe using the BISmark platform. So here's a graph that shows Comcast Power Boost. So we profiled 3 users in Atlanta. So the y-axis shows the instantaneous throughput, and the x-axis shows time. So what we see here is that user 1 has a peak throughput rate of about 18.5 megabits per second, which drops down to about 12.5 after about 14 seconds. Another user in Atlanta sees something similar, but sees 2 different peaks, and it comes down to the same long-term throughput value. But the third user sees a different peak too. So these are different service plans, I believe, in Comcast. And Comcast offers this as a service called Power Boost. So Power Boost is implemented using token buckets. Interestingly, the volume of the bucket that's used for all these 3 users is very similar, about 8 megabytes. So also, the short-term throughput is significantly different from the sustainable throughput. So what this means is that although the benefits are very good for short-term sessions like web browsing, if you're going to do a long-term file transfer, what you're going to see is the long-term throughput, which is about 12 megabits per second. So here's a look at last mile latency. So for this, we use data collected from the SAMNOS FCC study. So what we show here is a histogram of the baseline last mile latencies as seen by customers of these different ISPs. So the y-axis shows the percentage of users in that ISP that have a baseline latency within a particular bin. What we see here is that these cable ISPs, most of the customers of the cable ISPs see pretty low last mile latencies, less than 10 milliseconds. However, the picture looks slightly different for DSL ISPs. Actually have a significant fraction of users that see much higher last mile latencies. And we saw users with last mile latencies of greater than 40 milliseconds. So DSL last mile latencies can be high, and one of the reasons for this is that DSL ISPs employ a technique called DSL interleaving on the last mile, which is a technique which reduces loss in the last mile by adding more error correction techniques. So while this does have an effect in reducing loss, it unfortunately has a side effect of increasing latency. So finally, we look at another case study, look at modem buffers in home networks. So we profiled the buffering in modems by running a latency test, a ping to the last mile server, both while there's no traffic in the network and while the uplink is saturated. So the experiment ran as follows. So we ran a ping for 30 seconds, and then we saturated the uplink using IPerf for 60 seconds. So this is an AT&T DSL user, and the modem used was 2-wire. What we saw here was the baseline latency is about 10 milliseconds, and at 30 seconds when we saturated the uplink, the latency jumped up to about 800 milliseconds. So the y-axis is log scale. So we swapped out the 2-wire modem and replaced it with a Motorola modem, and we saw that the latencies were worse, about 1200 milliseconds. When we replaced it with a Vestel modem, we saw latencies close to 10 seconds. I don't think I need to say that at these latencies, the home network becomes practically unusable. And the interesting part is that it's very easy to induce these effects. All you need to do is have some user in your home network that starts uploading a large file, and the network becomes practically unusable for everyone else. Okay, so currently we have about 20 of these BISmark routers deployed in various locations in the US and about 10 in South Africa. And we are currently shipping these routers to US locations. We have plans to deploy them in Europe and Asia too, as soon as we can commission measurement servers in these locations. Although we only support the Netgear 3700 router now, we have plans to support the TP-Link 1043 and Atom routers. So, and we are interested in continuing research in this area, and we are interested in looking at performance for transit and access ISPs as seen from the edge. For instance, we are interested in looking at the effect of peering on performance. We are interested in looking at IPv6 performance, the effect of CDN location, traffic engineering, etc. on application performance. And we are looking for people who are interested to help us by deploying measurement servers. We'd also like to understand home networks better, for instance, the effect of wireless on end-to-end performance. And one particular question we are interested in looking at is when problems in the home network are caused due to problems inside the home network and not due to the ISP. So we'd like the community to get involved. You can help in multiple ways. You can host a BISmark router and get a nice high-end wireless router for free. You can host measurement servers in your network. We really want geographic diversity and locational diversity to ensure that we get reliable measurements. We're also looking for people to contribute to measurement tests. All the tests that all our code is open source and can be downloaded from GitHub. The username is BISmark-devel. And we're looking for people to contribute measurement tests. As I said, any test that you write, it can be deployed almost instantaneously on any router you'd like to. That's it. Please contact us if you want more information or are interested in collaborating. Thank you.
Very good. We have time for a few questions. Questions? Over here.
Hi.
Hi, I'm Amy Elkin from CenturyLink. When you were measuring the 6 meg at AT&T, probably you were measuring at the IP layer.
Yes.
So there was probably overhead.
Yes, but I've seen that with AT&T's DSL, the modem actually synchronizes at a slightly higher rate than the service plan rate. So I think that should take care of it. But yeah.
And then another thing about the latency, what matters is when latency impacts gaming or VoIP. And so the levels you were showing for DSL weren't high enough to really impact that. But if they exceed that. Yes.
Well, this is anecdotal, but I've seen discussions in some forums where people moved to UVers and they didn't expect a jump in the latency because of this issue. It's a shock. You think you're upgrading, but you actually get higher latency with higher throughput. Right. Yeah, so people do care.
Ben Jenks, Medius. Have you looked at using passive measurement techniques, looking at the traffic that's going through the modem?
We have discussed that. However, there are significant privacy concerns. So one thing that we're looking at is to get explicit permission from the user if they're willing for us to do passive measurements and then deploy passive measurements on a subset of these deployments. Yes.
Anybody else? Very good. Thank you very much.